Welcome everyone and good afternoon. We would like to welcome you at our Tech at Lunch webinar about a user-friendly toolkit we developed to select and design robust grippers for robotic systems. But first of all, some practical details. Your cameras and microphones are muted by default during this presentation. We encourage you to ask questions during this presentation in the Q&A chat box, and those will be answered during the Q&A session. And this presentation will be recorded and shared with you at a later moment. So it's not allowed to record this session yourself or share your recordings. Now, why do we focus on an assistive tool to develop robotic grippers? Now, when you consider the shift towards more customized products, as well as soft products like food or textile, and the deployment of robotic grippers in more dynamic environments, like, for instance, human-robot collaboration, you can see that the expected functionalities of robotic grippers are evolving rapidly and are pushing both industry and academia towards the development of more innovative robotic grippers. These developments are also endorsed by several market intelligence providers. They demonstrate that robotic grippers are still are a billion-dollar industry and are still have a growth potential for the upcoming decade. This should come as no surprise because companies are increasingly optimizing their production efficiency on their production floor by integrating industrial robots which interact with their environment by using robotic grippers as an interface. But besides those economical advantages, there are still some financial and practical challenges ahead. For example, no less than 50 to 70% of the total product cost is spent on handling, for which the gripper cost can even reach up to 20% of the robot cost. So the performance and the durability of a robotic gripper are strongly influenced by the properties of the part to be handled and the task to be executed. So a well-thought gripper selection and design is of significant financial importance. Nowadays, in industry, gripper selection and design are mainly done based on expert knowledge due to its intuitive, ad hoc, and time-consuming nature. More specifically, innumerable grippers of various manufacturers are on the market, and multiple selection and design criteria need to be taken into account. In addition, gripper selection is mainly done or is restricted to the portfolio of one specific manufacturer of robotic grippers and is confined to its most common grasping principles like jaw grippers or suction cups. Furthermore, when using a dedicated gripper to perform one specific task, for instance, grasping an object, the cycle time and robotic cell space will increase due to constantly switching robotic grippers from a tool magazine. So as a result, this approach is susceptible to additional costs, which are entailed by partially appropriate or over-dimensioned grasping solutions. Our toolkit tries to provide an answer to this by first providing a gripper selection tool, which is linked to a manufacturer-independent database consisting of more than 6,000 commercially available grippers, with the goal to assist inexperienced persons in a user-friendly manner. But for this, the standardization of grasping principles is required, as well as the standardization and limitation of selection criteria. This gripper selection will then result into a list of feasible grippers for the family of objects that are given by the user of our toolkit. These objects could range from 3D mechatronic parts up to 2D sheet metal parts, or even soft organic products. Then, in the second stage, the grasp optimization will find the most ideal grasping points on each object for all of these selected grippers. And this is based on quality metrics and constraints about the gripper and the object. And then finally, this will result into a gripper design that can handle all the objects of the same product family. For impactive grippers, which generate a contact force on the object, this means the design of fingertips. For restrictive grippers, which generate a force field onto the object, this means the design of a layout of individually positioned grippers, as illustrated by the picture down below. Then the importance of gripper selection has also been noted by several gripper manufacturers. They increasingly provide accessibility to their product portfolio by offering digital catalogs onto their websites, as well as assistive web tools. But with our toolkit, we would like to take this a step further by not only focusing on one specific gripper type, like impactive grippers, and also not restricting ourselves to one specific manufacturer. And this is done by first integrating this standardized tree diagram for conventional grippers as well as soft grippers into our selection methodology, and limiting selection criteria to the 35 most important ones, which we derived in close collaboration with our industrial partners, and dividing these selection criteria into 5 categories, ranging from the object to be grasped, the task to be executed, the environment in which the robot operates, the robot itself, and some gripper parameters. And this will result into a pipeline for our selection methodology that runs into 3 main steps. First of all, in the input stage in the back end, gripper data needs to be collected and stored into our database. This can be done manually or automatically by using web scraping of the digital catalog of gripper manufacturers. In the front end, the user has to specify certain values for the selection criteria he is aware of about his intended gripper or the envisioned use case. And then during the processing step, gripper selection is done based on rules which match the selection criteria with the grippers in our database. And this results into an interactive output. First of all, a 2D scatter plot in which you can interact, or a data table which allows some additional filtering and gives a direct link to the website of the gripper manufacturers. Then finally, in the table on the right-hand side, you can see an overview of the various gripper manufacturers and grasping principles that are currently stored into our database, which contains more than 6,000 commercially available grippers. And for this selection methodology, we created a standalone web interface that on the right-hand side allows some interaction with a 2D scatter plot and an intelligent data table. And a gripper selection is done based on the values for the selection criteria the user has to provide on the left-hand side. And the selection criteria are divided over the 5 categories I mentioned earlier. This 3D view allows us to provide some forces and moments on the gripper. And finally, we get a hit list of feasible grippers with a direct link to the website of the gripper manufacturer, where you can order the gripper or where you can get in contact with the gripper manufacturer's sales department. Then finally, I would like to mention that we also created a web API for our database and the selection tool, and which is linked with the design application you will see in a minute. But this web API could also be linked with your application as well.
Okay, hello everybody, and also good afternoon from me. The next step in providing a good gripper solution is then for the selected gripper that Jeroen selected with his tool is to make a good design for it. This falls into two categories. On the one hand, we will design fingers for the impactive grippers that were selected. And on the other hand, we will design layouts for the restrictive grippers, such as suction cups, which are selected by the selection tool. How do we do this? Well, this is a two-step process. First, we optimize the exact location on the objects where we want to make the gripper contact the objects. First, we need as input then the objects and the selected grippers of the selection tool. As a first step, we then reduce the objects to the feasible contact surfaces. So we find all feasible contact points between gripper and the objects. Next, for the restrictive grippers, we go then into layout optimization, where we first optimize how the layout of all the grippers needs to be in together. And then finally, for both impactive and restrictive grippers, we optimize the exact contact point where the gripper needs to make contact between the object. This For all these steps, we are helped by grasp modeling and quality measures, which take into account the physical properties of the gripper making contact with the object, and that way finding good grasps. As an output of this optimization, we finally get then the optimal grasp locations on each object for a certain gripper. As a first step, as I said, we just need to find the feasible contact points. Here I took an example of a 3D mechatronic object, which we want to grasp with an impactive gripper approaching from the top. This means that there are certain constraints placed on the object where we can grip it. If we approach this object from the top with an impactive gripper, this impactive gripper will have a certain maximal finger length. Let us say that this is this length, then you can see easily that this put a constraint that only the top surfaces, limited to here, are graspable by this gripper. Additionally, we also want to stay away from sharp edges, because we know from experience that a grasp at a sharp edge is bad for grasping. So that's why we also limit to all contact points which are far enough from a sharp edge, which are here indicated and recognized automatically as the lines in blue. Then next, we want to optimize the gripping locations. This first, for the restrictive grippers, we want to find the layout, optimal layout design. And for this, we need to generate first a lot of feasible candidate grasp for each of the objects. So say that we have 4 objects, we generate a large number, up to 200 or 500, depending on how big and how long you want to optimize for. Feasible candidate grasp for each object, and then we parameterize each grasp by the set of distances between the points. So here we are actually trying to find a layout of 3 points. So for example, 3 suction cups, and then we parameterize them by 3 distances between these 3 points on each object. Finally, we optimize then a common grasp, here depicted in the pink one, that is most similar to the best grasp on each object. And most similar here, we mean that the distance error between each of these 4 is then minimal to the common grasp that we find. This way, we then actually find the final layout design that we want then to place on each of the candidate objects. So next, we then want to find the exact locations where we will grasp the object in an optimization routine also. For this, for the impactive grippers, but also for the restrictive, but there's a slight twitch, which I will present in the next slide. We first start with the initial grasp and a step size S, which is a certain size. And then we find, for now, 6 new grasps in the neighborhood of the current grasp with this step size. For each of these 6 new grasps, we check the feasibility of the new grasp, and if it's not feasible, we remove it from the set. By the way, we selected the feasible regions in the first step of the full optimization procedure, we know that there will be at least one grasp always in a neighborhood which will be feasible. So we will never get an empty set in this step. For each of the new grasps, we then calculate the quality measure of these new grasp. And if any of them is better, then we replace the current grasp by the best new grasp and we start again to see if we can move further towards a better grasp according to the quality measure. If we didn't find any new grasp to be better, we check if our step size is already small enough. If it's not small enough, we first reduce the step size and see if we can find in a smaller neighborhood a better grasp in the same iterative procedure. If the step size is small enough, then we say our current grasp is actually our optimal grasp on the object, and we have found our optimal grasp. For the restrictive grippers, we actually follow the exact same optimization routine, only there the quality measure with which we measure how good the grasp is on the object, we now make it the distance between our candidate grasp currently on the object and the common grasp that we want to have as the layout of our gripper in the end. So this actually modifies the candidate object grasp to come as close as possible to the common grasp layout and thus create a gripper that can select all objects at the same time. Next, we want to actually also design the gripper itself from the best grasp location that we found on the objects. For 3D mechatronic parts, we mostly select impactive grippers. So for them, we want to design gripper fingers. We first do a classification of the optimal grasp locations that we found on the objects based on their local curvatures. This classification helps bring together equally curved grasp locations on the different objects. In this way, actually making the most similar grasps to be put on the same finger. Finally, we do a Boolean difference from a finger blank based on an ordering, also based on a curvature, and that way create an automatically designed finger. These are provided in STL format and can easily be 3D printed and also tested on your objects. For 2D materials, mostly sheet metal, but also other parts are possible. We calculate the base layout from these optimal found distances between the grasp points found, and then we map each of the object layouts to this base layout. And you can also see here in the top example that we can activate or non-activate certain of the grippers. For example, this gives a lot more freedom in your gripper solution. Otherwise, this thin object would absolutely not be able to be grasped with the same gripper as this much larger square object or this circle. But playing with the activity of certain grippers in your layout can certainly help this. Next, we converge all these solutions that we just presented, so the selection, the optimization, and the gripper design, into one user-friendly toolkit, which we will now demonstrate to you. So a first step that you can do with this toolkit is to obtain automatically the best selected grippers. For this, we first log into the database with credentials that you can get from us. If you provided anything wrong in the GUI, it will also nicely show you that it's in red, and if it's right, it will turn up green to make it nice user-friendly. Next, in the second step, you need to upload your objects. These are STL files that you need to load in of your objects. You can show the STL, and then next you need to provide some object properties that will help us gain a knowledge about the objects for the optimization and selection. Since this is a tool developed to handle product families, we want you to at least upload 2 different objects. That's why the submit button only becomes green after at least submitting 2 objects. Finally, you can also delete objects. This you can do by popping open the menu where you see all objects that you have entered and then selecting one and deleting it. Next, we want you to provide the use case specification. These are the selection parameters that Jeroen talked about for the gripper selection. And once you have submitted these, you can run the selection itself by clicking on Run in the selection panel. Then we give you the information about how many grippers were selected, and in the log file you can also see more about this. If you click on Show Grippers, you see the 5 top grippers that were selected, and you can also automatically go to the page of the commercial provider of the selected grippers. As a second option, you can also load in a gripper yourself. For example, if you already have a gripper in-house and you want only to do the design part for this specific gripper, this is possible by loading the gripper parameters of that selected gripper yourself. As a first step, you need to again load all your object data. And then in the selection menu, you can click the Load button for loading a gripper. And this opens the gripper specification menu. There you can select the properties for your specific gripper. And it shows you also when some things are not relevant anymore, they fall blank, and you also only have to provide the fields that are necessary. If you miss some fields, also here again, the color will show red and you can't submit a gripper. Also, submitted grippers can again be deleted in the same way as for objects. There's also another way you can load this information if you log into the database again. And the gripper that you have in-house is also in the database. You can, through the load menu, type your gripper name and find it in the database. Then automatically all the relevant information will be loaded in for your gripper. You only need to submit then the safety factor that you want and the maximum number of restricted grippers in your layout in the case of an restrictive gripper. By clicking Specify, the grippers are then checked against the objects. Next, we want to go into the optimization. So this is the next step in our GUI. After loading all the objects and running the selection, so having a selected gripper, you can click Run for the optimization. And then in the log file, you can follow the optimization itself. This can take some time, especially for a large set of objects. But the optimization file itself is after the optimization stored, so you can let it run in the background and you will not lose any result in the end. Next, we want to go to the design of the gripper fingers or the layout. This is the last panel in our GUI. And if you dare click Run, it will make either the finger design or the layout design. So here we have an example of a finger design where with show grasps, you can see the grasp that wants to be picked on every object. And then finally with show designs, we show the actual finger design that was made for your objects and selected gripper. These two can be exported to either JSON or STL. The JSON file contains all the grasp information of the optimal grasp that were found for the grippers. And the STL files contain the designed fingers. These you can then load into your preferred CAD software where you can adapt them to the base of the finger that you have, the base of the gripper that you have selected, or you can just 3D print them and test them out on your objects. So finally, as a conclusion, we had the goal of assisting inexperienced persons in a user-friendly manner to make an effective gripper design that can handle different objects of the same product family. And we have reached this by making a database and web interface for gripper selection and a desktop tool for gripper design. We tested it for both 3D mechatronic products with finger design and for flat sheet metal products with a suction gripper layout design. If you're interested in finding out how these two tools can help find you your next gripping solution, then don't hesitate to contact us in the future. This is a list of references that we also use for this presentation. And then I want to thank you for listening, and now we can go on to the Q&A.
Okay, thank you very much, Pieke and Jeroen. I think your presentation was very clear because we haven't received any questions yet. I would suggest to the audience, if you still have any questions, just send them to us. We will also send you the presentation and the recording of this live event, so you can watch it again. If you still have questions, just contact us. If you are interested in the GUI, you can of course also contact us. And then I'm going to give the word once again to Jeroen for the last goodbye.
Okay, so finally, I would like to thank you for your attention, and hopefully the demonstrated toolkit could be an added value to your future robotic application. So once again, please do not hesitate to contact us for future support. And by this, I would like to wish you a nice day ahead. And yeah, thank you.